Billions of tons of this are quarried every year, and demand is increasing. It could be limestone, granite, or marble, depending on what's available nearby, or what can be easily transported. It might be slag from steel making or power generation, or even crushed concrete from demolished buildings. Some of it has romantic names: blue metal, Canadian mahogany, beer stone, forest marble. It's less than 20 millimeters across and is always sharp and angular, so that it interlocks with its neighbors. And to make a road with it, you add bitumen, often called asphalt, to bind the separate pieces together. What you just witnessed happens millions of times every day, on roads all over the world. There's nothing you or we can do about it, except understand it better so that we can deal more effectively with its consequences. That's why Belron invests so much in research, more than any other glass repair and replacement specialist. As a result, we believe we know more than any other specialist or car manufacturer, which enables us to offer more to our customers. Let's start with what we know about damage creation. Most of us would say that a chip is created when a car or truck ahead of us kicks up a stone and fires it at our windscreen. In fact, it doesn't quite work like that. Look at this film from Carglass, our French business, and you'll see that the car in front throws a stone up into the air, and the car behind drives into it. In the 3D sequence we just saw, we weren't hurtling towards the car was hurtling towards us. So the things that make a chip are loose stones and a constant flow of traffic at reasonable speed to impart enough energy to the stone. Now let's take a look at chips themselves, with the help of Gwen Danielle of Belron Technical.
If we'd hit that screen a few years ago, the damage would probably have looked like this: round, smooth, a bit like a crater on the surface of the moon. We call it a bullseye break. Bullseye breaks are stable. In fact, you could drive around with one for years, so long as it wasn't in your line of sight. But bullseye brakes are rare these days because windscreens have changed. Glass is thinner now. Thickness has decreased by about 10% in the last 10 years alone. And this means that stone damage is much more likely to be like this. A star break. Star breaks have thousands of microcracks radiating from the impact point, some of which are invisible to the naked eye and all of which are potentially a lot more trouble than the trusty old bullseye. Now, here's Professor Kelvin Dunn of Swansea Metropolitan University to expand on our knowledge of the star break chip.
I use finite element analysis to model complex physical structures and visualize their behavior. Everything we know about the physical properties of laminated glass can be expressed mathematically, which means I can make a computer model that will behave the right way. Of course, you have to make sure that the computer simulation is accurately reflecting the behavior of the material, so we do what's known as calibration. Or in our case, building a gun and firing hundreds of stones at pieces of glass and filming and measuring what happens. We had to do this a great many times because we realized early on that all stones, all windscreens, and consequently every stone chip is slightly different. Happily, one constant is the PVB interlayer in a laminated windscreen, and I'll come back to why this is important later. Here is part of a laminated glass windscreen. I'm going to drop a ball on it to see what actually happens when it chips. And I'm also going to adjust the ambient temperature to see whether this makes any difference. Let's do the full screen. Ready? This is the chip at 0 degrees Celsius. Now let's see what happens when I dial up the temperature to 40 degrees. Three things happened. 1. There was more bending at 40 degrees. 2. The stress reached much further at 40 degrees. See the red and grey elements around the point of impact. And 3. More small pieces of glass were removed at 40 degrees, creating a bigger, more fragile chip. Now, this is not because the glass changes all that much, but because the PVB interlayer is very different when it's warm to when it's cold. When it's cold, the interlayer is stiff and the laminated windscreen behaves like one unit, resisting the impact, bouncing the stone right back, if you like. But when it's warm, the interlayer becomes much springier. This disconnects the two glass layers a little and allows the top layer to bend more when hit by a stone. This means the shock wave isn't so well dissipated through the whole windscreen, and the chip is therefore bigger. At 40 degrees, your laminated windscreen has almost become two separate sheets of glass, and the outer sheet isn't reinforced or supported so much by the inner one, which means that the same stone at the same speed will make a bigger chip in summer than winter. About 4 times bigger, in fact.
Thanks, Kelvin. So we know quite a lot about how star breaks are formed and how they differ at different temperatures. And we also know that windscreens sometimes crack. But what's the connection? Do windscreens crack because of these star breaks, or is it for some other reason? We began our investigations by asking this question. Does a little chip make the glass weaker? And if so, by how much? We asked the world's leading independent experts, 4 universities, well known for their materials science expertise, and no fewer than 6 independent research institutions around the world, including MIRA in the UK, CERAM in France, and TNO in the Netherlands. They took a lot of laminated glass samples and made starbreak chips in half of them. Then they put them in a calibrated 3-point bending machine to see what would happen. They discovered that glass with a chip in it is much weaker than undamaged glass. It has a reduced instant failure strength. In fact, the reduction can be as much as 70%. Put another way, if a piece of glass is damaged by a stone chip, it is much less able to stand up to the stresses and strains of driving. But why is that? We asked ourselves. What is it about a tiny little chip that so affects a piece of glass hundreds of times bigger than itself? Is there some special mechanism at work here? Well, the answer came from out of this world.
T-minus 10, 9, 8, 7, 6, 5, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis on a mission to build, resupply, and to do research on the International Space Station.
And is now in the proper alignment for its 8.5-minute ride to orbit, 4.5 million pounds of hardware and humans taking aim on the International Outpost.
The Space Shuttle's windshields cost $50,000 each to replace. Every second in space, millions of micrometeoroids hit the shuttle's windows at hypervelocities and make a tiny little chip. If one of those chips grew and cracked the windshield in orbit or on re-entry, the result could be disaster, which is why NASA insists on a very close inspection of shuttle windshields after every flight. They asked my company to develop equipment that would measure the stresses in the fused silica glass. They needed to know where the weak points were, how the glasses were standing up to the incredible strain of leaving Earth and then returning, or whether or not each windshield was flyable for another mission. As it turned out, we had to invent a whole new technology for this. We called it the Gray Field Polariscope, or GFP, and it allowed us to use polarized light to see what had happened to the structure of the windshield during the shuttle's journey. Here we are checking every millimeter of the windshields, and here's what the GFP allowed us to see. As so often happens, our work found applications outside the space program too. Bellrun have used our equipment on auto windshields, and this is what they found. Just as in the shuttle, a little chip focuses the stress of the entire windshield. It concentrates it, forming stress hotspots. You can see in this image, taken in polarized light by Edinburgh University, the lighter areas at the ends of the tiny cracks. That's stress. And here's another view, first of a chip in normal light, and second, using the GFP. Those red and yellow colors are high stress concentrations, and they're the reason why a piece of laminated glass is certain to crack if the added stress it's subjected to exceeds its instant failure strength.
So how do you add stress to a windshield? Well, by heating it, cooling it, or driving it. Minus 10 or 20 isn't unusual in Helsinki, nor in Chicago, Moscow, Copenhagen, even Edinburgh. And if you were to drive at 100 kph or so in Italy or Greece, some days would see the outside of your screen chilled to surprisingly low temperatures. On cold days, drivers switch on the heating and the screen demister, especially first thing in the morning. And an intact screen can resist this thermal shock. But what about a damaged screen? One that's up to 70% weaker? How long will it withstand the steep temperature gradient created by the outside cold and the inside heat. Not long. On average, in independent experiments, like the ones you may have seen at Best of Belron 2008, it was a matter of minutes. Hot weather is also a problem for windscreens. Drivers need their air conditioning in Dortmund and Dallas, as well as in Death Valley. Another steep temperature gradient that a damaged windscreen may not survive. In more independent experiments, cracking occurred quickly. And it was also found that some cracks grow in the sun without any encouragement from the air conditioning. The third hazard for a weakened windscreen is simply driving. Rough roads, bumping up and down curbs, speed bumps, they're all out to get a damaged windscreen, and if the chip and the shock are big enough, the inevitable occurs.
So we know that extremes of temperature and mechanical stress cause chips to crack. But we also know that most windscreens aren't always subject to extremes. We've all experienced chips that sit there for months, not growing at all, until the day the screen cracks for no apparent reason. What's the story here? Dr. Siegfried Fouvry of the École Centrale de Lyon has done a lot of work for Belron in this area.
Most people have heard of metal fatigue. It was first identified in 1842 when a train from Versailles to Paris crashed and one of its axles failed due to many small strays instead of one large one. A more famous example was in 1954, when 3 De Havilland Comet jet airliners fell out in the sky in the same year. The aluminium of the structure, subject to an accumulation of small strays that were focused in the sharp corner of a window in the fuselage, crumbled and gave away. And in 2005, Flight 101 from Miami to the Bahamas lost an anti-wind due to the repeated small stresses acting on a tiny crack in the metal. In our laboratory, we have been recently working to find out how the same effect operates in glasses. Although laminated glass has a different molecular structure to metal, a similar effect to metal fatigue can be seen. Look down a microscope with me at this animation of the leg of a ship. We can see individual glass molecules and the bonds at the tip of the microcrack. As we subject the glass to repeated small stresses, each one much less than would be required to cause an instant failure, the bond between 2 molecules fails, putting more stress on the next molecule bond. Little by little, molecule by molecule, the ship grows. Even in ordinary driving and subject to quite normal temperatures, accumulated stress will cause failure. Here is the same thing in a real test. We apply a stress continuously to a shaped sample until it cracked. At no time was the glass subjected to anything like its instant failure load, but little by little the chip grew and the glass cracked. Our research shows that a little chip will become a crack when the fatigue stress reaches a certain threshold value.
So we're left with two questions. When will failure happen? And what can be done to prevent it? No one yet knows the answer to question one. It could be any moment. It could be in 6 months. Every chip is different. Every windscreen is different. Every road, every driver, every summer and every winter are different. Although science does now know that every chip should become a crack, it doesn't know when. But there is some good news. Here's John Lesniak again with the answer to question 2.
When we discovered that stress is the key to broken windshields, the reason that a little chip can cause total failure in a large piece of glass, we also checked whether the converse is true, whether a repaired windshield has had its stress hotspot relieved. It would make sense, and it would explain why glass repair is so effective at preventing further cracking. Here is a stone chip as seen through the GFP. There's the stress at the ends and around the edges of the brake. And now here's the same chip after repair. No stress, no hotspot, no likelihood of catastrophic failure or fatigue.
We're about the size of a grain of glass debris at the bottom of that chip we so carelessly created half an hour ago. A technician is about to repair us to get rid of our stress hotspots using a system that's exclusive to Belron. Don't be alarmed. He's putting a special primer into the brake to aid adhesion, mix with moisture, and check that he can reach right to the ends of the cracks. Now that's the vacuum disc above us, sucking out dirt and moisture with the primer. Now, the key to Belron's system, the RAS 123, is placed over the brake. The RAS is able to create a vacuum and high pressure in the brake, which delivers a better repair. We're at the vacuum stage now. No air at all in the brake. And now we switch to pressure as the resin is forced in at 4 atmospheres. The brake is filled and the resin is cured with ultraviolet light. Let's check what's happening at the molecular level. Affected and energized by the ultraviolet light, the resin molecules attach themselves to the walls of the windscreen chip and form a chemical bond with the glass. Now they cross-link with each other, building a microscopic matrix of incredible strength that supports the chip as well as fills it, relieving the stresses in the glass. The repair is complete. The windscreen should never crack from this chip. And we have saved energy, waste, time, glass, and money compared to the replacement that eventually would have been required.